Here are our notes for Chapter 9, Fluid Mechanics. We'll start off by reviewing some ideas from chemistry, and that's the difference between solids, liquids, and gases. Solids have definite shape, they cannot flow, and they also have definite volume. By this we mean they are incompressible and they don't naturally expand unless they are dramatically heated up. Liquids take on the shape of a container, they can flow, and they're classified as a fluid. Liquids also have definite volume. They're very, very difficult to compress, and they don't expand much under when the temperature changes. Gases take on the shape of a container. They can flow. They're classified as a fluid, and their volume changes depending on the container that they are in. For all three of these states of matter, we can compute density, and density is just mass divided by volume, where mass is in kilograms and volume is in cubic meters. The symbol for density is the Greek letter rho. This is a lowercase rho. For solids and liquids, density is independent of pressure because the volume of a solid or liquid does not change when the pressure changes. For a gas, the density changes significantly when pressure and temperature change. Let's do an example. Find the density of a cube of an unknown substance. The mass of the cube is 35, this should say grams, and it has an edge length of 1.2 centimeters. Convert the density to kilograms per meters cubed. So our mass, in this example, is 35 grams, which is equal to 0.035 kilograms. The volume of a cube is equal to the side length cubed, which would be equal to 0.012 meters. And then I'm going to cube that side length. And when I do, .012 cubed is 1.728 times 10 to the negative 6 cubic meters. Then my density will be mass over volume, or 0.035 over 1.728 times 10 to the negative 6th. So that's 20,255, and I'm going to round to the proper number of sig figs, which would be 3. So that's 20,300 kilograms per meter cubed. Moving right along, let's talk about buoyant force. Buoyant force is the force that acts upward on a liquid submerged in a liquid or floating on the liquid surface. The buoyant force is listed as FB, and the buoyant force will equal the weight of displaced fluid or the mass of that fluid times 9.81. If the weight of an object is greater than its buoyant force, it will sink. If the weight of the object is less than or equal to the buoyant force, it will either float where it's placed or float on the surface. The volume of a submerged object is equal to the volume of the fluid displaced. The volume of a floating object is not equal to the volume of the fluid displaced. This provides a way to determine the volume of irregular objects when trying to determine the density. Archimedes' principle says that any object completely or partially submerged in a fluid experiences an upward buoyant force equal in magnitude to the weight of the fluid displaced by the object. I'd like you to imagine a glass of water and an ice cube. What happens when I take that ice cube and I put it in the water? When I put it in the water level should rise. If we think about how much the water level rises, or if I think about the volume of this shape I've created, that volume of displaced water is equal to the volume of the ice cube that's under the water. So again, the volume of the water displaced is equal to the volume of the ice cube that is under the water. The buoyant force on this ice cube, we know two things about it. First of all, the ice cube still has weight, but we know that the buoyant force balances the weight of the ice cube. They are equal and opposite. We also know that this buoyant force is equal to the weight of the water displaced. And I could compute the weight of the water displaced if I knew the volume of this water and its density. If I knew its volume and its density, I could get its mass and therefore get its weight.
Let's use some lab equipment to take a look at what happens when an object floats in water. This is an overflow can. You can see water pouring out of the spout at the top after I put a piece of wood in the top of the overflow can. The water is flowing into a beaker so that I can measure the amount of water that is flowing. It turns out, you'll have to take my word for it, but it turns out to be about 50 milliliters of water displaced by the piece of wood. I can measure it with a graduated cylinder. Now I'd like to see what happens if I put, oh, there's my 50 milliliters. And now I'd like to see what happens if I put mass on top of my wooden boat that's floating there in my overflow can. Can you think about what would happen if mass was put on top of that floating piece of wood? I'll give it a try here. Oops, I lost it. I'm going to give it another try. I have another mass. This mass is 20 grams. I'm going to find the center of gravity and place it gently on top. And you can see the water pouring out of the overflow can. The question is, how much water will flow out of that can? I'm going to empty my graduated cylinder so that I can use it to measure how much water flows out of the can. Here we go. Sure enough, it's 20 milliliters of water. I'm trying to zoom in to give you a better look, but it's really difficult to see up close. 20 milliliters of water, and now just to prove to you that I did use a 20 gram weight, and just a reminder that the density of water is 1. So a 20 gram mass must displace 20 grams of water in order to float, and that corresponds to 20 milliliters of water.